All right, physics in general can be broken up, I'm going to break it up, into three main things. There's physics, typically you take physics 1, and then there's physics 2, and there's physics 3, right? So what do we cover in physics 1? I'm going to expand on this stuff, over the next several minutes, but essentially physics 1 are all of the concepts associated with motion. Motion, force, and energy. Now, everybody watching this has some idea of what motion is, things that move, right? And what a force is, when you push on something, right? And energy. You might have an idea of energy, but that's usually a little bit sketchy, or people aren't quite sure what energy is, but we know it has something to do with motion or with doing something, that kind of thing. And that's typically true. But the idea here is we're going to drill down into these areas, and we are going to 110% go into every one of these topics and define them to understand what we mean in physics by force, motion, and energy, so that when we solve our problems, we know what we're doing with each of our equations, with each concept. Now, typically after you finish all of this up, which is quite a bit of material, we're going to get into more detail about that in a second, you talk about physics 2. And these are arbitrary definitions, but typically in physics 2, you learn about a big word that scares a lot of people. It's called thermo. What do you think thermo means? Like a thermos, it means heat, right? Or temperature. Thermodynamics. Whoops, I can't spell dynamics. Dynamics. Right? Thermodynamics and waves. So in the broadest sense, physics 2 is going to be about dynamics means changing, thermo means heat or temperature. So it's all about things that are changing, temperature, changing heat, and also what kind of work can we get out of that. So you think about a car engine, you combust gasoline in the piston, right? Or in the piston chamber. That explosion releases heat and it pushes that piston. So the concept of heat, which is coming from that explosion, right? And the concept of the piston moving, which is doing work able to push the car, those are interrelated things. So thermodynamics is all about heat, energy. How do we transfer that into work that we can do on the environment? How can we build a machine that somehow uses heat energy and get it to do some work? And there's a lot of details there that we'll get to, but that's what it basically is. And we talk about waves. We have water waves, we have sound waves, we have energy that we can transmit via a wave. If I get a jump rope and I kind of oscillate it, I can send energy down the rope to impact a wall or whatever it's tied to. So we're going to talk quite a bit about waves. And then we break up the class into physics 3. Physics 3 is actually my favorite part of physics, but I like them all. But physics 3 is my favorite part, and that is electricity and magnetism. So electricity and magnetism. There's some other topics in here. Now, when I say electricity, we are going to learn a little bit about electric circuits, batteries, circuits, voltages, current, electric current, things like that. We're going to talk about that. But really, the main part of electricity and magnetism, we're going to learn about magnets. We're going to learn about the magnetic field that surrounds a magnet. We're going to learn about the electric field that surrounds an electric charge, like an electron or a proton or some other charged particle. So we have this thing called electric fields and magnetic fields, and they're kind of like peanut butter and jelly. They're not exactly the same thing, but they're definitely related, and the equations that govern both are very similar to one another. So really, in modern physics, we've unified electricity and magnetism into one thing called electromagnetism. And it turns out, if you take an electric field and a magnetic field and you oscillate them so that they're kind of a combined oscillation, what you end up getting is an electromagnetic wave. So it's a wave that travels, that has an electric component and a magnetic component, and it travels, and guess what that is? That's light. So I have lights here. They're hitting me, they're bouncing off of me, they're going into the camera. Those are all electric magnetic fields that are oscillating, hitting me, and bouncing off. So we're going to talk about the wave aspect of light after we talk about electric fields and magnetic fields, right? And then this is kind of, you could call it physics 4, but I'm going to call it modern physics, which is something you typically see also, modern physics. And this is actually one of my favorite parts also, because I just find it mind-blowing. The first part of this typically is relativity. I'm sure you probably heard about this, and I know that you also probably heard about something called quantum mechanics. what is all this about? Relativity deals with the fact that's just mind-blowing, but the fact that clocks, things that we think are constant, tick, 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 tick of a clock. Time is not constant for all people when they're moving near the speed of light. So if I have one clock stationary and one clock stationary next to it, and they're ticking in synchrony, right? And then I take one of those other clocks and I zoom them off near the speed of light. When that clock is traveling near the speed of light, time doesn't flow the same for that clock or that person in the spaceship. It flows differently. In other words, the reason it's called relativity is because things happen differently to different people or different experiments depending on how you're moving, how fast you're moving. Now, we don't notice clocks ticking differently because we're not traveling anywhere near the speed of light. We're traveling at a snail's pace, but that's the way the universe works. Everything's relative, including the ticking of clocks. And then we have the idea of quantum mechanics, which we're going to get into a whole lot of detail later, but quantum mechanics is all about the fact that, I told you, electromagnetism was a wave, right? But we also have figured out in the 20th century that it does behave like a wave. Light does behave like a wave, but it also kind of behaves like a particle, like an object. Instead of, it has characteristics of wave, but it also has characteristics of being a little particle. So is it a particle or is it a wave? It turns out it's both. We don't have a word for it, but real photons, real electrons, real protons, real tiny particles of anything have wave-like characteristics, and they also have particle-like characteristics. So it kind of messes with your mind because it doesn't make sense, but it is the way the world works because we have over 100 years of experiments showing that both of these things, relativity and quantum mechanics, are both, as far as we can tell, absolutely true. Now what we want to do is jump a little bit more detail. We're going to get in the entire course into so much detail, solving tons of problems, but I want to give you a roadmap to show you a little bit more about these topics. And we're going to get a nice overview of that. So when we talk about motion, first thing we're going to actually talk about in physics are the equations. The equations of motion. And to simplify it further, we're going to actually talk about motion only along one direction, one dimension we call it. So we're not going up and down, we're only going left and right because it makes things simpler at first. So you'll see 1D motion, you'll see you have 2D motion when you have like a throwing a ball up in the air and also horizontally. And then of course we'll have 3D motion, which is the real world, when things can move left, right, up, down, backwards, and forwards. But really the equations are all very similar. So we start out by talking about what happens in one direction, only when the object can only move basically backwards or forwards. And I'll tell you, this thing called equations of motion scares a lot of people, but you already know a simple equation of motion, and that is what? What do you know about velocity? I know we haven't really talked about velocity in this class. We're going to talk a whole lot about velocity, but you already know that in a car, when you're driving, it's miles per hour, right? Or kilometers per hour, right? So the velocity that you're traveling is the distance over the time. How far did you go? How long did it take? You divide those numbers, you get something called a velocity. Now, if you remember a little bit of algebra, this is a fraction, so I can actually get rid of the time on the bottom by multiplying left and right-hand side of the equation by time. So on the left-hand side, I can get velocity multiplied by time, and on the right-hand side, that will be just distance, which is left over. Now, if you don't totally understand how I got there, this is just a little bit of algebra. I multiply the right-hand side by time, which cancels time and time, leaving distance. I multiply the left-hand side by the same thing, time, so I have velocity times time. This equation makes sense also because when you think about it, if I know that I'm traveling down the road at 45 miles per hour, we don't typically use miles in physics. We're going to learn about meters and all that, but if we're going a speed or a velocity of 45 miles an hour, and I'm traveling down the road for 2 hours, how far did I go? Think about it. I'm going 45 miles every hour, and I'm multiplying by the 2 hours because, every hour I go another 45 miles. So that should be clear that this is 90 miles that I've traveled. This thing here, distance is equal to velocity times time. That's just a very simple equation of motion. So don't let these words confuse you or scare you. Equations of motion, it sounds really difficult, but you already have experience with basic equations of motion. You know that the distance you go is going to be how fast you're going times how long you're traveling at that speed, how the time involved. So what we're going to do as we go on is we'll just have more complicated cases. We're going to figure out, well, what's going to happen when I have gravity involved if I'm dropping something? What's going to happen if I throw something? What's going to happen if I have friction, right? Then the equations of motion are a little more complicated, but it's the basic same idea. So for instance, in 2D motion, I might actually throw something like a baseball or something. I might throw something up here at like 39 meters per second. So I'm using the same thing. It's a velocity, but it's meters instead of miles, meters per second. So you all know that if I take a ball and I throw it at an angle, right? So let's say I'm throwing it at some angle here. I'm going to call that angle theta. That's just a variable that's talking about the angle, or I can just take out the variable itself and just say, well, I'm tossing it at 25 degrees from the ground, right? What's this thing going to do? I mean, you all know that if I do that, it's going to continue up, it's going to hit some maximum, and then it's going to come down, and it's going to hit the ground again. So the question is, if I throw a ball at 39 meters per second at a certain angle, what do I want to know? Typically, I want to know how high did it go? That's what I want to know. How high did it go? And I want to know generally how far did it go? And I'm not going to write it on the board, but I also probably want to know how long was it in the air. So that's called projectile motion or 2D motion, and it's just going to be basically an equation of equations of motion applied to that situation, right? Now what we're going to actually do to solve these kinds of problems is we're going to take this 39 meters per second, I'm going to blow it up for you down here. If I throw something at an angle of 39 meters per second, right? And I'm throwing it at some angle relative to the ground, 25 degrees, let's say right here. It actually is kind of complicated to deal with 39 meters per second at an angle, right? All at once. So what we typically do is we actually break the 39 meters per second at that angle, we break it up into two parts. We break it up into how fast is it going horizontally, right, the horizontal part of the motion, and how fast is it going up and down, the vertical part of the motion. So I might have, as a result of this, I might have a vertical part. See, it kind of comes over to where the tip of the arrow is. So this is going to be a vertical part of that motion, and this is going to be a horizontal part of the motion. So what I'll do is I'll apply the equations of motion, which we'll learn later, to the up and down motion by itself, and then to the horizontal motion by itself, because anytime you throw anything, if you throw it steep, if you throw it shallow, you can always break the motion into horizontal motion and vertical motion. So it's easier to solve these problems by solving the horizontal part separate from the vertical part. So we're going to learn about that. And this concept here, splitting it up like that, that's called a vector. And we're going to learn about vectors in great detail because they're going to be one of the big tools that we use in our tool bag to solve problems. Now the next thing we learn in physics typically is the concept of energy. And I know that most everybody here has an idea of energy, but we're going to talk just a brief minute about energy. So the best way I can describe energy is, or at least one type of energy, is a roller coaster. So here's a roller coaster, very high hill, and then comes down to the bottom, and then a little bit like this, and then maybe it just kind of does something like this. So there's a car, it clink, 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 gets to the top, very, very, very high, right? At the very top of this very high mountain, right, we say that it has a high potential energy. High potential energy. I don't have room to write out potential energy. But the reason it has potential energy at the top is because we're in a gravity field. So if you bake something very high off the ground, if you were to drop it, it has a high potential to accelerate down to the ground and to hit the ground, right? So to do something, to hit the ground and have to do some, impart some energy into the ground. So we say it has a high potential energy here. So what happens is the roller coaster goes to the very bottom, and all of that potential energy you have, because you're accelerating, when you get to the very bottom here, when the roller coaster starts to round the bottom down there, we say that we have a high kinetic energy. So we're going to learn a lot about potential energy and kinetic energy. Kinetic energy is how fast you're moving. It's the energy of motion. So you know when you get to the bottom of the trough here in the roller coaster, you're going fastest. Up here you're going slow. So you have very low potential energy here, high potential energy here, and it's all converted into kinetic energy. And then here, over at this part, what do you have? Well, you have medium potential energy, because you are a little higher off the ground, but not as high as here. And you have medium kinetic energy. because you're not going quite as fast as you were down here. You bleed off some of the speed. So one of the big things we're going to do in physics is we're going to talk about the total energy of a system. And the total energy of a system that moves like this anyway is the potential energy plus the kinetic energy. And the total energy of the system actually doesn't change, because whatever I start the system out up here at the top is how much energy I have. It's just all in potential energy form. So at the very top of the hill, I have a very high potential energy. That's what the up arrow means. And I have a very low kinetic energy up at the top here. But then when I get to the bottom here, I have a very low potential energy because I'm basically at ground level. And I have a very high kinetic energy because I'm going really fast. So you see what's happening? Every time the potential energy gets high, my kinetic energy must get low. And every time the potential energy gets low, the kinetic energy must be high. So it's like a trade-off. It's like 2 cups of water. I'm pouring the water in here. Now the energy is over in the potential energy cup. Then I pour some of the water back in over here. Now the energy is all in this cup. And if I pour half and half, I have half of my energy in the potential energy cup and in the kinetic energy cup. That's basically here. So the trade-off between potential and kinetic energy can be used to solve tons of problems. And we're going to spend many hours solving lots of problems involving potential energy and kinetic energy. Okay? It's one of the big central core topics of physics. Then we're going to talk about the concept that I know you've heard about, Newton's laws. Whoops, let me go and spell Newton correct. Newton's laws. Newton's laws of motion. So what Newton's law says, basically, is, well, there's a few laws of motion. We'll talk about all of them. But the one that we're going to use to solve tons of problems is F is equal to ma. So this is the force on something is equal to the mass times the acceleration. What this thing says in layman's terms is that if I push something with a force, like if I push something, then it has mass, obviously, because it's made of matter. If I push something, then it must accelerate. That's all it says. It's common sense. You know this stuff. I mean, physics seems really difficult, but you know this. You know that if you push something, it's going to accelerate. If I have a bowling ball and I'm forcing it, I'm using my hand to impart a force, then it's going to leave my hand in motion. And as I push it from rest, it's going to have to accelerate, which means it's going to speed up from some non-moving velocity up to some speed, right? So this F equals ma is going to be used to solve a great many problems. And then after we talk about Newton's laws for a while and solve tons of different types of problems, we're going to talk about Newton's law of gravitation, which is a really big deal, obviously, because we live on Earth and there's gravity here. What does this mean, though? If we have a planet, we're going to call it Earth, and we have a moon here we call M. So the Earth has some mass, we call it M1, and the moon has some mass and we call it M2. What Newton figured out is there's a force that exists between any 2 pieces of matter. It exists between you and your pencil. It exists between a lamp and television. It exists between the Earth and the moon. Any 2 pieces of matter pull on each other with some force of gravity, and that force, if the distance between these 2 things we call r, that force of gravity is equal to some number g, which we'll talk about. It's called the gravitational constant, time mass 1 times mass 2, so we're multiplying all the masses together times g, this number, and on the bottom it's the distance between them but squared. So you might hear this called the inverse square law or something like this. So if the Earth's mass gets bigger, m1, then the force is bigger. If the moon's mass gets bigger, the force is bigger. But if we increase the distance between them, like if we stretch out the Earth and moon even bigger, then since it's in the bottom, we're dividing by a bigger number, so the force actually goes down as we make things get farther and farther apart. So this is called the universal law of gravitation. Now, we actually know now that Einstein, a couple hundred years later, released and invented his theory of gravitation. And his theory of gravitation is actually more correct than this one. But still, this is a really good starting point to understand gravity, and we're going to solve lots of problems using Newton's form of gravity because it's a whole lot simpler than Einstein's theory of gravity, which is beyond the scope of this class. But just keep in mind that, you know, this was accepted fact for 250 years or so, and now we know that it's not quite right in some instances. And in the early 1900s, Einstein published a theory which totally reinvented how we look at gravity completely. But you might ask yourself, if I push on something, it's going to accelerate, then if there's a force between the Earth and the Moon here, shouldn't the Moon come crashing in to the Earth? Shouldn't it come crashing into the Earth? Well, of course it should. Absolutely. And that's the famous thing, you know, Newton sitting under the tree and watching the apple fall and having, who knows if it's true or not, that's the story, right? He realized that the Earth is pulling on the apple and the apple falls down. He realized maybe the Earth is pulling on the Moon with the same force. Well, then why is the Moon not crashing down like the apple? That's the real question. But he thought, well, maybe it's possible that gravity is extending all the way to the Moon and pulling on that. And the answer to the question is, it is pulling on the Moon, and if the Moon were not moving, it would crash into the Earth. However, the Moon is actually moving. It's moving sideways with some very high velocity v. So it's going round and round and round. It is being pulled in, but it's going so fast in the horizontal direction, for lack of a better word, that's called the tangential direction, that it never really hits the ground. And you say, how is that possible? Well, I have a little prop here. It's not a great prop, but it's a little prop. So this is like the Moon here on the end of my little wire. Well, if I take this guy and start spinning it around, what happens here? Well, you see it's going round and round and round and round, just like the Moon is. But what am I doing with my hand in the center? Look carefully. I'm actually pulling on this thing. So what I do is when you start it off, you have to start swinging it, right? Like I'm swinging it, and then I get it to go around once. And then I get it to go twice. And then then once it's going horizontal like this, I'm pulling on it. I'm pulling it straight into my hand. But it never hits my hand because I've given it a very fast speed horizontally like this. And that's basically the exact same thing happening with the Moon. If the Moon weren't moving at all, if it just stopped, then it would accelerate straight down and hit the Earth. But only because it's moving so fast horizontally can we escape that. Okay? So now we talked about gravitation, right? Newton's law of gravity. And then, after we talk about gravity, we talk about collisions. Collisions in physics. And what do I mean by collision? I'm saying, what happens when you smash two things into each other? Like, let's say I have some mass, m sub 1, and I have another mass over here, m sub 2. I don't know what the masses are, but this could be 5, and this could be 25 or something. It could be different, right? And then this thing is going this direction at some velocity v1. It could be like 100 meters per second or something. And this guy's going in the opposite direction, v2, and it's a different velocity. So different masses and different velocities, they smash into each other. Well, what's going to happen when they bounce off? What is the velocity of this guy going to be when it bounces off? What's the velocity of the other one going to be? And which direction are they going to go? And what if I don't smash them head on? What if I smash them at an angle so that they fly off at an angle, you know, like billiards or pool table? So all of this stuff has to do with collisions, which involves the concept of momentum. So we're going to learn how to calculate the momentum of this ball and the momentum of this ball, and we're going to use a law of momentum to figure out what's going to happen after the collision. So that's basically wrapping up what we generally talk about in what we call Physics 1. Now I told you Physics 2 was what we call thermodynamics and waves. And so what we're going to do is talk about that briefly next. Learn anything at mathandscience.com.